So, welcome. Well, let me start this very brief introduction by mentioning that one of the invited speakers for the workshop asked me why we had, or how come we had so many probabilists in Brazil. And I told him that the way it works here, and with most areas of mathematics, is that you have a few pioneers who go study abroad, and they come back, and communities are built around them. So here we have a pioneer from the probability community, Antônio Galves, from full professor at the University of São Paulo. He's been, for many years, he was very active in the area of interacting particle systems, and which is an important area for mathematical research in Brazil. And in recent years, he decided to move on to topics that are still quite probabilistic, but also related to statistical inference. First, he did a lot of work on chains of variable length, and applied that work to linguistics with some interesting statistical results. And then apparently he decided that that was a bit too easy, so he decided to try the hardest area of all, which is to study the brain. So for some years now, he's been doing some quite interesting work on neuroscience, both on the mathematical side, on trying to model the brain, and on the statistical side, which is to infer brain characteristics or brain function from signals of all sorts. And I guess his talk today will be about the latter. It's called Retrieving a Hidden Context-Free Model from EEG Signals.
Well, I'm glad to know that I'm a pioneer. I don't think it's a complicated situation to be a pioneer. But thank you very much for considering being a pioneer. The other day I met Claudio. I was having dinner with Claudia, and Claudio said, he was with his wife, and said, Antônio Galves is the grandfather of probabilistic theory in Brazil. Okay. So, much better, much better. No, he did not say, but he said he is at the origin, the father of my father, so the grandfather. So you see, here I put neuromath, and I will start with some kind of advertisement about the Center for Neuromathematics. So this I joined to work with many people, Aline Duarte and Guilherme Ost, PhD students in São Paulo. They are now at L'Aquila with Enrico Presutti. Ricardo Freimer, Freimer is the one who is at the origin of the ERPEM, and Claudia Vargas is here. She's a neuroscientist. And okay. So this is part of the project Neuromath. So I'm putting the website of the center. That's old. So let me tell you a few words about the Center for Neuromathematics. So it starts with the idea that we need new mathematics if you want to make a theory of the brain. And this idea, well, it's not new. 20 years ago, David Mumford, who is a famous mathematician, he got the field medal 25, 30 years ago. He starts working himself in neuroscience. I remember that long time ago here, in this same room, I heard a talk by David Mumford about the fact that we need new mathematics to make a theory of the brain. So that's the long-term goal of the project. And this needs two things. One, which is to create a new class of mathematical models. So Roberto Imbuzir spoke about interacting particle systems. But the class of system which exists now, it's not enough. So that's why people like Enrico Presutti and Evelo Scherbar and myself and Pablo Ferrari were trying to do something new. And also we need the statistics for these new models. So that's maybe the reason for which my talk entering this session on high dimensional statistics or whatever. So this is what we want to do. And now I must tell you that we are not a center of applied mathematics. We are not. And we are not because we don't have the mathematics which is required. So applied mathematics means I have mathematics and I use this tool. And we don't have. So unfortunately, so people have been trying to develop new mathematics for neuroscience since the 70s, I guess. In the 70s, there was a big effort with great people like Bela Bolobach, like Daniel Arment, like Chuck Newman. And by the way, Bela Bolobach and Chuck Newman are members of the scientific board of the Center for Neuromathematics. But these efforts in the 70s were developed on a quite naive basis. You say, okay, instead of speaking about spin, speak about neurons. It's not the same thing. So they did probably interesting mathematics, but without any effect on neuroscience, any effect at all. The big problems remained untouched. So that's the situation. David Mumford made an effort in the 90s, and he made interesting contributions. He started using Bayesian statistics to develop this. For some reason, I don't know, he stopped. Now he's no more doing this. But I guess that's the moment for mathematicians to become interested in neuroscience, because we have a huge amount of interesting complex data. Huge amount. We have very detailed descriptions of phenomena occurring in the brain. And now we need to invent new mathematics. What I'm going to do today, okay, I respect all these Nobel Prize models, and yeah, we are not signal processors, because most of the neuroscience nowadays is just signal processing, which is very useful. We do it also, but this is not the problem. The problem is that we need new models. We will need new models. So, mutatis mutandis, which means if you change what must be changed, our goal is something like find a Gibbs model, but for the brain. So something which is sufficiently simple to be analyzed on a rigorous basis, but it still have some of the properties displayed by the brain. Okay, so that was the advertisement moment of the talk. Okay, now the neurobiological problem. So you have two stochastic sources. I will show to you, in our case, what is. And the first question is, do stimuli of different sources produce distinct brain process? So that was a starting point, because the kind of data, electrophysiological data you have here, is in our case electroencephalographic data, EEG data. And so this is functional data. You have something like 2 to the power 7 functions evolving time at the same time. We have 128 what's the name? Electrodes registering EEG data. So the first idea was, okay, this is a problem of classification of functional data. I had worked with this kind of data, not for the brain, but in linguistics a few years ago with Ricardo Freiman. We used the projective method to treat this. Okay, let's try to classify and to see if the stochastic process produced by the different stimuli, if this stochastic process can be classified in such a way that all the EEG which have been produced in different trials by source 1 are put in one class, which is a different class from the ones which have been produced in different trials by source 2. And then, in the middle of the work, we realized, as a matter of fact, Claudia realized something more deep. It's interesting that in this case, the basic intuition was not produced by a mathematician, it was produced by a neurobiologist. So we realized something much more interesting, and that was a surprise. So I will tell you something which starts in a very humble way and become a very ambitious project. And that's the question. Do the EEG data say anything about the structure of the source? And this is a difficult question. So let me try to justify the question. So I will justify the question in the blackboard. And the question is, say, a conjecture, which probably was given originally by David Mumford. So let me quote David Mumford. I don't know if he wrote it in this way, but this was his original idea. And the idea is the following. The brain is a statistician. And what he does is just statistical model selection. And this means the following. So when I see you in this room, I'm trying to understand the structure behind these collections of signals I'm receiving. I remember Siddhartha Ribeiro, famous Brazilian neuroscientist, giving a talk to São Paulo, and he said, well, I had class of ski, we say in English, and then I was sleeping, and all my body during my dream was doing again my movements. And somehow I was compressing the expression, the impressions I had during my lesson. So what we say that learning constitute memories. All this is just trying to understand the structure of the source which produced the data. How could I argue in this direction? So if the brain is really understanding the structure of the different sources, how could I see this? Well, if you find the structure of the source in the EEG data, this is quite an evidence in this direction. So that is the motivation. If you wanted to ask me questions, I'm going to speak about some things which are a little bit exotic. So if you have questions about any word I apply. Now, I'm going to explain to you what I mean by structure of the source. I guess I want to okay. So the stimuli, each stimulus is a sequence, well, the stimulus are independent samples produced by 3 different stochastic processes. For me, source is the same as stochastic process. And it's realized as a sequence of acoustic events. And the acoustic events are of 3 types: strong beat, weak beat, and silent unit. So more precisely, I have, the random signals are not IID, the samples are IID. I produced a sample of a stochastic process, I produced another sample, I produced another sample. The sample are not IID random variables. They are independent sample of the same source. So each sample is formed by, so G is the index of the sample. And 1, 2, 3, N are the N successive acoustic events. And I have the corresponding, so you see I have a complicated notation. So 1, 2, m are the m different realizations of stochastic process. Si is the name of the stochastic process. And the index here, the stochastic process is a sequence of symbols. The symbols are strong, weak, or silent. And then I have the EEG data, which is a function, a continuous function, taking value in RD. D here is 128, is the number of electrodes I have in the brain. Okay, more precisely, each source is a probabilistic context tree. So I guess some of you maybe does not know what mean a probabilistic context tree. So I will explain to you. So let me see what I put here. Okay. Now the source is the following. First source. So on. That's very monotonous. So let me write it. So 2 is a strong bit, 1 is a weak bit. So this is just a waltz. Boom, pa, pa, boom, pa, pa. But what I offer is just this kind of sound. It was synthesized. But then this is not interesting because in this case, all the samples would be the same. So I want to put some randomness. So I decide for each symbol 1, I decide to erase it. And then it becomes a 0, or to keep. And then it remains 1. And I erase with probability epsilon. And I keep with probability 1 minus epsilon. And I do this decision for the symbol's weak bit in the IID way. Now my sequence becomes something like, say, I erase this one, this becomes a 0. I erase this one, this becomes a 0. Now the question is the following. Let me try to imagine an algorithm to produce these symbols. I want to describe the simplest possible algorithm to decide which symbol to put in the next step. Okay? So that's very easy exercise of context tree models. Now I want to decide, so this symbol, let me call xn this symbol. So I'm here in step n. I want to decide which symbol I will put here. And so I look back, step n minus 1. And then I find here the symbol 2. If I find the symbol 2 in the step n minus 1, then it's clear that the next step will be either a symbol 1 or maybe a symbol 0, because I decide to erase the 1. And then next will be either 1 or a 0 with probability 1 minus epsilon or probability epsilon. Now, let's suppose that the symbol I find here is 1. Well, if it's 1, I don't know what to do next. Because it could be this one here, the first one, or it could be this one. And the situation is different. If it is the one which comes immediately after 2, next symbol is 1 or 0. If it is the one which comes 2 steps after 2, next symbol is 2. So what I do here, I must go a step back, go to n minus 2, and see if it is 2, 1, or 0. And if it is 2, I know that the next symbol will be 1 or 0 with probability 1 minus epsilon and epsilon. If it is 1, I know that the next symbol will be 2 with probability 1. And if it is 0, it's the same. So I have a situation in which the number of steps I must go back in the past in order to produce the next symbol is variable. It changes as a function of the past itself. I could write it in a better way, like a tree. I have a picture this way. This kind of object was created by a fellow named Jean-Marie Sanin in a seminal paper produced in 1983. The title of the paper is A Universal System for Data Compression. He created this not for make statistics, but to compress data. And then he created a very, 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 very flexible class of process, which actually it's a good candidate to approximate any stationary chain, stochastic chain. And it's interesting because this idea that you have a stopping time back in the past, which tells you how many steps back in the past you must go in order to be able to produce or to predict the symbol. This is something in between Markov chains, which have always a finite memory, and the class of chains with memory of infinite order. As an exercise, I give you the following. Let's suppose you have here a source producing a code, say a bulb, a light, producing light, which is 1 or not, 0. Call this yn, and here you have a window which could be open or closed, and call this cn, and then you have here an observer. Which could see the light or not, and call this Zn. And then Zn is just y of n times c of n. Okay, assume c of n are IID random variables, not 1/2 and 1/2. Assume yn is a order 1 Markov chain. So this is just observing a Markov chain with noise, and the noise could erase the signal. And now, what is this? Is this a Markov chain? No, this is not a Markov chain. This is a chain of infinite order. And you must go back in the past until you find for the first time light in Zn. So if you try to understand how to predict next symbol, the probability that Zn plus 1, Zn to be equal 1, if you ask how to predict this, if I know all the past. So you need to go back to the past until you find, for the first time, you find 1. And what occurs first is useless. And that was the idea of Jean-Marie Sanin. He said, in most scientific data, to predict next symbol, you don't need to go infinitely many steps back in the past. Usually you don't. But you cannot say that it's enough to go 1 step, 2 steps, 3 steps. So the number of steps typically changes. It depends on the past. So if you fix the number of steps, if you say, no, let me go back to the past just 1 step, so this is very bad. If you say, well, 1 is not so good, let's take 10. You don't do statistics, because with 10 steps in 2 symbols, you have to go back 1,024 steps in the back. Don't do statistics. So it's an impossible situation. So the idea that the number of steps you go back in the past can be treated as a random variable, a stopping time, actually, back in the past, is a genius idea. So you see, in a simple vault, you find the same situation. So you have another source, which is the following. It's a simplified samba. It's a simplified samba, so Roberto Museu says samba of Paulista. Yes, and produced by a German guy living in Rio de Janeiro. So 2, 1, 0, 1, 2, 1, 0, 1, and then you erase some 1. So you have these 2 sources. And you produce independent samples of it. The idea is that nobody receives the same sample of the other volunteer. All the volunteers receive samples produced in a random way using the sources. So let me see what I put here. I don't remember. So in this notation here, I have a tree. So you see the tree there. The tree, here I put a tree. I write this like a tree. So that the present moment is the root of the tree. I go back in the past. If I have 2, it's enough. That's a leaf. If I find 1 or 0, I must go back another step. So this is a partition of the past. So in this model, I have 2 ingredients. I have a tree which tells you what are the concluding strings of the past, the partition of the past which you need to observe in order to predict the next symbol. And P, well, P is this. It's a decision to have 1 or 0. So in any case, this is P. By the way, as an exercise, in this situation here, what is the tree? So it's easy to see that the tree is this one. It's an infinite tree, 1, 1, 0, 1, 0 square, 1, 0, k, and so on. Okay. So the structure of the tree is given by a tree of the model, by a tree, and a family of probability measures which tells you what is the probability of the next symbol when you are in a certain branch. Reasoning called this strings of the past, he calls these strings context. So in his original paper, he speaks about a tree machine or context tree models. So all sources, a vaults and a samba, simplified, can be represented by 2 context tree models. An important thing is that if you are a statistician and I give you not the description I gave, but the sounds 2, 1, 0, 1, 1, 0, 2, and produce really, you are able to retrieve the tree. So reasoning proposed an algorithm he called the context algorithm, which does it in a consistent way in linear time. And since reasoning, several persons, including Roberto Museu and myself, have been trying to produce the different algorithms to retrieve it. So you can do it. You, human being, statistician, you can do it. The question, is the brain able to do the same thing? Is the brain able? is the brain able to do the same thing? Can you retrieve the structure of the source from the EEG data? So you know what is an EEG? You put electrodes in the scalp, and you measure the variations of the potential in the extremities of the electrode. Each electrode measures millions of neurons. So what you have is a very local mean field description what's going on. You can hear not the details of your voice, my voice, but you can hear the global voice. So if I'm closer to the electrode, my voice will be more so the voice of the thousands of millions of people around can be listened. So you can see what is the global activity. For instance, you can see if we start shouting at the same time. So like if it was outside Maracanã, Sunday afternoon, trying to understand what was going on inside the field. So you can realize when someone made a goal because, So if people say, so say almost. If people start shouting, you can imagine that maybe the referee did something. So that's what a EEG does. We have 128 electrodes, and you just register the electrode during the volunteer is exposed to the data. Okay, so this is a problem of functional data classification. And as a matter of fact, nobody knows how to model EEG data. That's if you ask a signal processor, he say, no, Antonio is wrong. I can do it using autoregressive models. But this is just a very naive approach. But because most of things you are observing is noisy. So you don't have any reasonable model for EEG. So that's why I start thinking about using the projective method. Okay, so I explained this already. That's the tree for the waltz. For the samba, that's the tree for the samba. And also we have to make a break, you have the IID, 1/3, 1/3, 1/3 source with no structure at all. So the tree is reduced to the root. And now that's the ideal volunteer with the electrode in her head. And well, we propose either a sample of waltz, IID, samba, or the other one. So this is just a kitchen recipe. Now, okay. Now, you have two kinds of silent units. The one which is constitutive. So you see in the samba you have pam, pa, pa, boom, pa. The third, so you have two. In the samba, the basic cell is this one. So this is what we call V0. I don't know why V, so why V, Claudia? There is some reason for the engineer to call this. This is what we call V2, and this is what we call V1. But now, attention, I could quite well erase 1 with probability, in our case, with probability 0.2, and the one erased becomes a 0. And this I call miss. So a miss is a silent unit which was produced by erasing a weak bit. So this is the data. It's quite difficult to understand something. I remember when I started studying statistics a long time ago, my teacher said, well, have a look at the data to see if you see something. I don't see anything here. Maybe, and if you have good eyes, you could see here V2, V1A, V0, V1B. So V1A is the first one, V1B is the second one. You have 2 bits, 2 weak bits, and so on. Here you have a miss. You have a V2, which was to be followed by a V1A. Actually, we decide to erase it. Okay, so the idea was to use the projective method. So I have a few slides describing the projective method. So the projective method is the following. The idea is very clear. In order to present the idea clearly, I must say something which is wrong, slightly wrong. So forgive me. I will tell you why it's wrong in a minute. So now you have a functional data with a function which is random. So I have functions produced in an IID way by 1 or 2 or 3 sources. So I have all this set of functions. And now I want to test if all the functions were produced by the same source or not. So I have this function here, and then I have this function here. So I gave the functions to you. Look, that's a sample with 1,000 pieces of function, continuous function, and this is another sample. Could you please tell me if the 2 samples have been produced by the same source? You said, well, unfortunately, I don't know how to use things like Kolmogorov-Smirnov test for functional data. You know Kolmogorov-Smirnov test for real data. Do you? Don't you? Okay, this is a test Kolmogorov himself invented during the war, I guess, to help the effort in the war against Nazism. He invented and the idea is that there is a distribution, with the distribution of the Brownian bridge. So you could test if something is from the same source or not with real numbers, comparing the distributions, the empirical distributions, with the empirical distribution of the Brownian bridge. So that's a genial idea he had 70 years ago. Kolmogorov himself, the great Kolmogorov, the great mathematician of the 20th century. So the problem that Kolmogorov did it for real numbers, and here you have functions. Now, the idea of the projective method is quite simple. Let's suppose, so now I'm going to tell you something which is slightly wrong, and it's an exercise to find why it's wrong. So take the unit ball in the function, in the set, in the space of the functions I'm considering. So you take the unit ball, and then you choose a direction in this unit ball in a uniform way.
It's not an exercise.
Well, this is not possible because the unit ball is not compact, so you don't have uniform distribution. But if we had a uniform distribution, you could use it for in dimension 10. So you choose a direction at random, uniformly. So without choosing more than one direction and another one. And then you project all your data, the 2 samples, using this direction. Now, the result is the following. For almost all choices of your direction, if the Kolmogorov-Smirnov test that now you can apply for the real data reject the null hypothesis that they have been produced by the same source, then the same is true for the functional data. The idea is it would be really unlucky that you choose exactly the direction in which the difference disappears. Maybe there is a direction in which you destroy everything, but well, unlike man, if you choose exactly this one. So that's the idea. Now, there is some kind of technical things. This project, this method was invented by Ricardo Freiman, Juan Cuesta, and David Baldwin 10 years ago. From a formal point of view, 8 years ago. And well, I used it some time ago. So that's a theorem. You could ask me, how do I choose a random direction since the uniform ball is not compact? Okay, use a Brownian motion. Realize a Brownian motion and make the projection over the Brownian motion. And this plays the role. Just because you need a Gaussian measure. So the Brownian motion is the easiest way to do this. Okay. But the intuition is exactly what I tell you. It would be really unlucky if you decide to use the direction in which the difference disappears, because you choose it at random. Okay, how to apply it? You consider the EEG signals as realization of points in a Hilbert space. So you have now two sets of elements in Hilbert space, the realization of the waltz, of the samba, and the null hypothesis that they came from the same source. You always fight against yourself. So the null hypothesis, there is no difference. And then, well, you must do some kind of filtering. For instance, when you are recording EEG, if you blink your eyes, all the data explodes. So this goes to plus infinity, minus infinity. So we must filter all this. But when you do this, the data is bounded, has a maximum and minimum. And then Kahneman's condition, which was the one, is satisfied. And then that was the original idea. Let's use the projective method to classify. But then we realized that you could do something much more interesting, which is to retrieve the trees. Okay. So that's the conclusion. And then it's interesting because you finish with, by suggesting you a new mathematical object. I don't know many things about it. So first thing, you remember the picture I showed you. Here. So you have a natural segmentation of the EEG data which corresponds to its acoustic event. So the first one is a strong beat. The first beat which goes immediately after strong beat, the silent unit, and so on. So you have these pieces. So we can segment the EEG data into several pieces so that each individual stimulus corresponds to a specific event. And for instance, both Ms and V0 correspond to silent units. So a first naive idea would be the same, would be the following. Your EEG data only express... Clube Atlético Mineiro? It's a happy man today. You could imagine that the EEG data only express something about the nature of the acoustic event which produced it. That would be a kind of naive idea, like a snapshot of what happened. So if you have a strong beat, this makes a strong EEG record. If you have a weak beat, let's make a weak sound. If you have a silent, you don't have anything. And if it is the case, the EEG would be entirely useless because it would be only a translation of the stimulus. And in this case, why to do all this? Because from a structural point of view, Ms and V0 are entirely different. Remember, Ms is an omitted weak beat. V0 is a constitutive silence. You see, this is V0, is the silent unit which makes the samba be a samba. Pum, pa, pum, pa, pa. Instead of pum, pa, pum, pa. That would be a kind of pum, pa, pum, pum. And then João Gilberto developed this missing, constitutive missing to the point of perfection. But even a very simplified version, this zero is crucial to make the pum, pa, pum, pa. But you could erase. I'm developing. But you can also erase a 1, and then it becomes a 0, and this is a miss. So again, the EEG data. Is the brain aware of the distinction between erased units and silent units? Is our statistical tool able to catch this difference in the EEG data? In other words, is the distribution, the empirical distributions of miss, different from the distribution of V0? So the data, we put together all the V0 here and all the miss here. Okay, so what we do, that's the way to implement. So instead of just looking one direction, it's better to choose several times several directions and make and project several times, and then to look at the average. So this is what I'm putting here. And DW, EMW is the projection of M and W using the direction WI. And for each I, we define ZI if you want, if you reject or not. And okay, so that's the way we test using the projective method. So preliminary results. Using the projective method, 11 volunteers. So we tried several things, but I'll tell you after. Reject a null hypothesis. This one, we reject it. So we see that Ms and V0 are different unities. And also, we did it to test if the first weak beat in the samba and the last weak beat in the samba, if they have the same law or not, and they don't have. And also in the waltz, the pum, pa, pa. So the brain attribute different distributions, produce samples, produce EEG data with different distributions according to the position in the structure. Okay, so the analysis of the data is in progress, but now it suggests an object to us. hidden context tree models, also called hidden stochastic chains with memory of variable length. So that's the conclusion. Okay, I have 2 minutes, I guess. I use. Good, I have 5 minutes. Now, you know that there is an object, a famous object in statistics and probability, which is called a hidden Markov model, HMM. This object was introduced in the literature in the 60s by, I guess, by Bow and Petrie, in the 60s, by Bow and Petrie. But the one who really used it was a genius named Rabiner. And Rabiner was an engineer working in AT&T. And Rabiner was trying to make a mathematical framework for broadcast transmissions, signal processing in acoustic signal processing, linguistic acoustic signal processing. And then he realized the following thing. So when I say, well, A is A, you say A, you say A, I say several times A. Every realization of this A is different. Yet the phoneme behind, for everybody is clear, is A. So I'm realizing a phoneme say A, but it has acoustic realization, which display an intrinsic variability. Intrinsic variability. The same person repeating the same phoneme several times produce the variability. Produce it in different ways. Okay, so there is the following idea. The phonemes are in a set. The phonemes are in a set. The phonemes are in a set, say, O, finite set of all phonemes. It was a little bit H, finite set of all phonemes. H come last hidden. Then I have a stochastic chain describing the succession of phonemes. And this is our stochastic process. And I said, well, let's consider the simplest one. Let's consider this is a stochastic order 1 Markov chain. So let's try to make a model for the succession of phonemes as a Markov chain. Okay, it's a very simplified model, but let's use it. But then the problem is that every time I realize a phoneme, I do it in a different way. So he said, okay, to each to each object, to each phoneme here. So this is a phoneme. You have a probability measure. That's a probability measure on a set V. So V is a set of acoustic realization, continuous set of acoustic realizations. Then you have here your discrete time, discrete finite set of symbols. This is Markov. And then for each symbol here, you choose, using distribution Pxn, you choose a realization Y of n. These symbols are in the set H hiding. These symbols are the set V visible. And this is a hidden Markov model in which you display a continuous realization in a set of visual, of acoustic realizations chosen with a certain probability. Okay, there is something which is clearly naive in all this, is the fact that the way you pronounce, you produce the phoneme depends not only of the phoneme itself, but also depends of the structure in which the phoneme appears. So I guess Rabiner probably could have invented this object 50 years ago. He didn't. For some strange reason, when you look at the literature in hidden Markov models, what are the questions they ask? If you have the sample, can you find the number, can you find all the constitutive elements, which is the transition probability of the Markov chain, the family of probability measures translating each hidden symbol in a visible symbol? You can also ask the following question: can you infer the number of hidden objects from the visible data? But nobody apparently had the idea that more than looking at the hidden object to decide what's going on, something else is at stake here. And this is what our experiment tells us. So let's think again. Ms and V0 are silent units, but one is constitutive. It should be there, otherwise it's no longer samba. And the other is just to make things more interesting. They can be there or not. And the brain realizes this, and the brain produces different signals you register in the EEG data according to those things. In other terms, the brain realizes the position in the structure of the chain which is behind. Exactly the same reason for each 2 weak beats. The first weak beat and the second weak beat are not realized in the same way. So the brain is not translating the acoustic quality of the sound in something like EEG. The brain is identifying the structure behind. Okay, let's put this in mathematical terms. And that's the conclusion. So you have a context tree model, a context tree model. This is given by a tree of contexts I call tau, and also by a family of probability transitions which tells you what is the probability of having a symbol when you have a certain context. But now, and all these take values in a set A, which in our case is 0, 1, and 2 in our example. And then you have here another set, which is the set L2, 0T, which corresponds to the segmentation of the EEG data. And then for each context, which is a context, which is a string, you have a P of W, which is a probability, which is a probability in a Borel set associated to L2, 0T. So you have a probability measure on the set L2. And then what you produced as EEG data is the realization of this hidden context tree model. So as far as I know, this is a new object in the literature. I have been looking using Dr. Google to advise me. So you find things, Roberto, like hidden context model in which the context is not important. The context is just to replace Markov by variable length, but yet the distribution depends only on the symbols. There is a recent paper by French people, exactly, Thierry Dumont. So I don't understand why this so obvious idea did not show up. I must admit that myself, it was Claudia and Aline Duarte, my PhD student, who realized that this difference means that you are using the context. I was unable to imagine this 1 year ago. So now you can see the following things. The classical question, how many hidden symbols do you need? In the EEG case, there has a very obvious answer. You have the pieces of EEG. These are functions. Use the best tool of cluster analysis you have at your disposal. For instance, use Luc Devroy-Camins cluster tool and classify your EEG pieces. And if you find like in the case of the waltz, if you find 7 leaves in your tree, if you find, 7 clusters, this tells you that your tree has 7 leaves. So this is an entirely new idea. I don't know how to extend it behind the example of the EEG, because here we are using the fact that you can segment the data. But I'm telling you that in the beginning I said that neurobiology needs new mathematics. And this is an example which surprised me, because when we started, we said, well, let's use again the projective method just to classify data. And then the evidence of experimental evidence obliged us to consider that there is a new cluster of stochastic process. I don't know how to study stochastic process by now. I only know how to use it in the EEG data. But I guess this is something we should do in the next months. Thank you very much.